So today I want to talk about Verilog, and this is going to be a lecture that's particularly useful for the lab. So let me begin by saying that in your lab kit you have FPGAs, so field programmable gate arrays, which are essentially sort of general purpose circuitry. So what an FPGA is, it's really like a set of logic cells that are embedded in a general routing structure. So these little boxes here are the logic cells, and as you can see, they are connected to one another in some way. The connections are more dense between neighboring logic cells, and they're less dense between logic cells further apart. But by and large, this is a very very repetitive structure, essentially. And each of the logic cells contains, typically a 6-input Boolean function calculator and 1 bit of memory. And the key thing here is that all the features, like all the connections and exactly what logic is used, etc., is electronically reprogrammable. So this is general purpose in the sense that you can sort of activate some of these connections and some of these logic functions such that you can instantiate or build any circuit that you want. And that, of course, makes it very useful for our lab. Okay, so how are you actually going to use FPGAs? Well, what you're really going to do is you're going to write code in a language called Verilog. And this language essentially allows you, or this Verilog code essentially allows you to do two things. So maybe most importantly, Verilog essentially generates a bit stream, the streams of 0 and 1s that get sent to the FPGAs and essentially make and break connections in that FPGA. So you set the programming bits in the FPGAs such that you make the desired connections and the desired logic as specified by the code. But the second aspect of Verilog that's also going to come in handy is that it actually is a simulation language. So whatever you specify in Verilog, you can also simulate to verify that the system that you're intending to build actually behaves the way it's supposed to build before you build it. Okay? So this lecture really is about Verilog. So Verilog is, as I said, a programming language for describing hardware, and allows you to simulate behavior before you're wasting time in implementing something that might be wrong. It allows you to find bugs early. And it also sort of enables the tools to automatically create the implementation of the circuit that you want. It's a little bit similar to C or Java or other programming languages, although it's not quite the same because it really specifies, it's really a hardware specification language. There's different versions of Verilog. We're mostly using systems Verilog here. Okay, so let's start by looking at an example of what Verilog looks like. And specifically, this is structural Verilog. And structural Verilog is called structural because in this approach, you essentially really specify exactly the circuit that you want to create. So as it's shown here, so this is an example code for the circuit that's drawn at the top of the page. So these dashes here, this is a comment, as you may have guessed. Module, sort of like a function in Verilog, defined here as a keyword. So this function has the name AOI, and or invert in this case, and it has several variables. You have to say which variables are the outputs and inputs. So here we're saying output is F and inputs are A, B, C, and D. The order up here in the function doesn't really matter, but you have to keep track of which variables you're assigning to be outputs and inputs. Okay. Another key word here is this assign. And essentially with this assign command, you're really just specifying actually the circuit. So you're saying your F here is equal to not A and B. So this is not and or, not A and B or C and D. And of course, you have to close the module using end module. So again, so assign, it's really, let me rewrite that here. It's a continuous assignment. But basically means is that F changes when the inputs change during the simulation. Okay, so that's the first example of structural Verilog. Okay, so this is the exact same circuit, logically the exact same circuit again. I just made one change here, which is I've introduced a new keyword called wire, which is exactly what you think it is, and it specifies a wire connecting other logic elements. So here I sort of taken this previously more compact function, I'm breaking it apart into its components, and I'm saying I'm defining this first block here, so assign AB is A and B, that's of course this module up here. Assign CD is C and D, that's this part down here. Then I'm assigning this intermediate wire O to AB or CD, so that's this. And then finally F is just the inverse of O. That was the previous one, and now F is not O, is here, right? So these wires will come in handy in the sense that it's often convenient to kind of, make smaller functional pieces and then connect them together. It's actually can be much more intuitive in terms of the design. This is yet again the exact same system, but now I'm introducing a few additional keywords, namely and, or, and not. And the point here is just to say that Verilog has a sort of a range of built-in functions. So and, or, not, what else? NAND, NOR, XOR, etc. are keywords in structural Verilog. So there's a range of these keywords. There's more than I'm giving you here, but it's just convenient to be aware that many of these sort of commonly used functions are actually built into Verilog, and you can just call them from there. So here, instead of using this assign statement to define or create a new function, I'm just referring to these existing keywords. Everything else is exactly the same as before. Okay. Now, as we get to more complicated Verilog structures, of course, it's convenient to sort of combine multiple modules or to call modules from within other modules. And this is what we're going to do in this slide here. So the device that we want to build here is a 2-input multiplexer. So we will talk about multiplexers much more later in the class, but the basic idea of this device is that you have 2 inputs wire, I and J, and 1 output, and there's a selection input that allows you to choose which of the wires gets connected to the output. So it's basically either J or I the data coming in on either J or I is transmitted to the output. And which one is chosen, that is determined by the selection input. Okay? Actually, it doesn't matter so much here what it does. The major point here is that this 2-input MUX can be built using this predefined AOI module that we've created earlier, and it's restated here for convenience. So again, the top half of this code essentially just says, redefines the module that we already have. And then the interesting part comes down here, where we define a new module called MUX2. Again, this module has a few variables. So the output is V, inputs are select or cell I and J, and then there's 2 wires that are connecting, that create internal connections. Okay, so just to clarify, so input, select, and J sort of are external connections sort of to external world, and then this wire cell B and VB are essentially internal to this module. Okay, so then just looking at this structure, you can sort of see how this 2-input MUX is built. So there's this NOT, also of course a function built into Verilog. It's called, you give all of these modules have names. So here they're called G1 for the NOT module. The AOI module here has the name G2, and this other NOT has the name G3. You can define what the inputs and outputs are to this specific module with this specific name. One thing that's going to be interesting is this notation here with the dot F of V of B. So I should say that you could have also written something like that. AOI G2 of VB I select cell B and J, and this also works. The advantage of using this notation up here, so which actually looks more cumbersome, is that position here doesn't matter. What you're saying with this statement is that in the position of the variable that in the module definition is called F, you're going to place VB. In the thing that was called A, now you're gonna put I in its place, etc. When you use this notation, you do not have to worry about about the ordering of the variables, which can be very convenient if you somehow forget what the ordering was, like if you have multiple, if you didn't name things perfectly logically, or if somehow this you just forget. With this particular notation, any order will work, because it will go, the new name will sort of be put in the right location. With the down here, if you change VB and I, it won't work as you intended to work. But the basic message here is that essentially you can define modules and then call those modules from within other modules, kind of creating hierarchies of increasingly complex logic functions. Okay, so now that you're essentially, you know how to write or describe simple functions in Verilog, you want to test them. And these test benches, I think, will be extremely useful in the lab. So I think you'll write many, many test benches in the exams. And the purpose of a test bench is essentially to check whether your system, whether your design works before you actually realize it in the FPGA. Okay, so again, there's a few sort of key features that I want to introduce here. So importantly, so again, you define a module. It's called mux2 test, so it's meant to test the multiplexer module we just introduced on the previous page. It doesn't have any ports. It's important for the test bench. We're introducing this new keyword, reg or register, and we'll sort of see in a second what that is, but it's sort of important within an initial block, as we find here. You're going to use register as opposed to wire. Outside of initial blocks or outside of always blocks, generally you could use wire. So it's okay. So it's kind of similar to wire, but not quite, in the sense that the wire variable actually specifies a physical wire, while a register is essentially just a variable that changes its value in response to a change in an input. Okay, so what do we have here? So this command initial sort of initiates the testing, and then you say begin, and you're setting your input values or your register values to certain values. So here you're setting selection to 1, I to 0, j to 0. Then you're saying this hashtag 10 here means wait for 10 time units. Wait 10 time units. So it's a time delay. And after that, switch I to 1 and keep the other ones as the same. Another 10 time units later, switch selection to 0, and another 10 time units later, switch j to 1, and then end. Okay? So that's basically what you're doing here in this block between begin and end. Is essentially you're providing a series of stimuli to your system where you sort of go through different combinations of inputs that are hopefully sort of indicative of how the system should behave. Okay? And then here you're saying, well, I'm going to take these inputs and feed them into my multiplexer. And eventually here, in this next initial block here, I'm going to print sort of the result of this analysis. So basically what onto the screen, onto the console. Okay, and what should you get here? Well, this is showing what the actual result should look like. So here, in this first column, you have the time. Then here you have selection. Here you have I. This is J. And this is V. Okay? So let's see that it all makes sense. Let's walk through this. So at time 0, I set the selection input to 1, as specified here, I to 0, j to 0, so that's what that is. And V is 0, basically meaning that the way this multiplexer is set up is that if I'm setting the select input to 1, I choose to copy the data from incoming channel I. Okay? And so you can see that after 10 time units, when I'm setting I to 1, well, obviously I changes in this column here, but the output V also changes. So this kind of suggests that, okay, as long as I have my selection input set to 1, I'll just copy whatever input comes in on I. Then, when I'm switching the selection input, as it's done in this column, so after another 10 time units, I'm setting selection to 0. So now I'm supposed to copy the data coming in on channel J, and channel J in this case is 0, so output is 0, which is correct. So this was good, this was good. And then the last thing I have to test is, well, what happens if I switch J to 1 and I keep the selection input set to 0? Well, then again, the output follows J and goes to 1. Okay, so that's the basic idea of a test bench. So it allows you to send in to simulate the behavior of your module by you send in a set of stimuli, of inputs that should allow you to characterize the behavior of the module, and then you can check whether the output actually does what you want it to do based on the definition.